We're told a gallon of milk is at 68 degrees Fahrenheit and it's placed in a refrigerator. If energy is removed from the milk by heat transfer at a total rate of 0.08 BTUs per second, how long would it take for the milk to cool to 40 degrees Fahrenheit? And we're also given the specific heat and density of the milk, respectively here. This is information you could look up, for example, in a table. So our system here will be the milk. So let me just draw a dashed line around the milk. And we're interested in how long it would take to cool off. So there's some energy being removed by heat transfer. So I'll just draw it this way, Q out of the system. So to figure out how long it's going to take for this to cool down, this will be a first law analysis because I'm interested in getting to a particular temperature. That temperature is related to the internal energy. So the internal energy is changing because there's some heat transfer. So that's a first law type of analysis. So let's write out the first law. And since I'm interested in the time involved, I'm going to write down the first law in terms of a rate equation. So rather than delta E, I'm going to write dE dt, and instead of a Q, I'm going to write a Q dot. And this is going to be written as out of the system. I'll come back to that in a moment. And then I'll write the rate of work done on the system. So a few things here I'm just going to highlight. First of all, it's a rate equation. This is the time rate of change of total energy in the system as opposed to delta E, or the change in total energy. This is the rate of heat transfer rather than just heat transfer. And this is the rate of work rather than just work. Here I've written this as minus Q dot out of the system because I know that we have some energy being removed. So I'm just writing it as a minus Q dot out. And this number, by the way, will be equal to minus 0.08 BTUs per second. That's given in the problem statement. And then this is the rate at which work is being done on the system. Since we don't have any change in volume here, there is no PDV work. We don't have, I'm going to assume that the milk itself is incompressible so that there is, in fact, there's zero change in volume. We don't see any paddle wheels or springs or electrical work being done. So this is going to be zero. So there's no other work happening. And then lastly, the time rate of change of total energy in the system, that's going to be like the time rate of change of internal energy plus kinetic energy plus potential energy in our system. But since we're not dealing with a milk jug that's flying around the room, there's no change in kinetic energy. It's not changing elevation, so there's no change in potential energy. So in the end, what I end up getting is the time rate of change of internal energy of the system is equal to minus Q dot out of the system. And again, we're given what this Q dot out of the system is. This is going to be a minus 0.08 BTUs per second. So now let's expand out the time rate of change of internal energy in the system. So I'm going to assume that I'm dealing with an incompressible substance. So assume the milk is incompressible. That's a really good assumption when you're dealing with liquids like milk, which then means that a small change in the internal energy would be equal to the specific heat, which in general is a function of temperature, times a small change in temperature. So that's the expression for an incompressible substance, in addition to the specific volume being a constant. So this is, again, a small change in the specific internal energy is the specific heat, which in general is a function of temperature, times the small change in temperature. Now I'm going to also assume that the temperature change is relatively small because we're going from 68 degrees Fahrenheit to 40 degrees Fahrenheit. So a change of 28 degrees Fahrenheit. So that means the C is not going to change very much over that range of temperatures. It's a small range of temperatures. So I'm going to assume that C is a constant. So I'm going to end up writing this as du dt. I'll also divide through by a small change in time. Is equal to C, which I'm assuming is a constant, times dt dt. Okay, so I'm just assuming, let me make a note here, assume C is a constant, and that's since change in temperature is small. In general, the specific heat does change with temperature, but over this small range, it's pretty reasonable to assume it's a constant. And then I'm also just dividing through by dt on both sides, so I get the time rate of change. And then lastly, if I want to get it in terms of internal energy, notice here this is specific internal energy, here it's internal energy, then what I'll do is I'll just multiply through by the mass. So the change in internal energy would be the mass times, let me put an intermediate step here, it'd be the mass times du dt. The mass is a constant, so I can bring it outside the derivative, and then it would look like this. So then I can take that expression and plug it in right up here. So I'm going to get mc dt dt is equal to minus q dot out of the system. And then I can rearrange that. Now it's in the realm of mathematics. I'm just now solving this differential equation. Oops, this should be divided by. We have that. I'm going to integrate both sides as I go from some initial temperature to a final temperature. Now, the rate of heat transfer is a constant. The mass, of course, is a constant, and the specific heat is a constant, so they can all come outside the integral. So the integral is just acting over the time. Now, if these things varied with time, I'd have to keep them inside the integral, but here they're not varying with time. So this is pretty simple to do the calculation. So this would be T2 minus T1 is equal to minus Q dot out of system divided by mass divided by the specific heat times, I'll just write it as delta T, just the time change. And this is what I'm trying to find. I'm trying to find that. So here we have all the information we need, right? So we know T1 was given as the initial temperature, which was 68 degrees Fahrenheit. T2 is the final temperature, that's the 40 degrees Fahrenheit. The Q dot, the minus Q dot would be, so this whole minus Q dot would be minus 0.08 BTUs per second. The mass we were given up here as being, we have to do a unit conversion. We're given that it's a gallon of milk, and we're given the specific, or we're given the density. So to find the mass, it would be the density times the volume. And here, the density is 64 pounds mass per cubic foot, and the volume is 1 gallon. So there's some unit conversion that would have to take place here. If you do that unit conversion and do the calculation, then this will end up being, the mass is 8.58 pounds mass. So we know the mass, and we're also given the specific heat. We're told that that's 0.94 BTUs per pound mass degrees Rankine. And we can convert these temperatures over to degrees Rankine as well. You don't really need to do that here because you're dealing with the temperature difference, but if you did want to convert it over to degrees Rankine, this is 40 degrees Fahrenheit is 500 degrees Rankine, and 68 degrees Fahrenheit is 528 degrees Rankine. You don't, like I said, you don't have to do that because this is a temperature difference, but it's fine. You know, you're always safer if you convert to an absolute temperature like degrees Rankine or Kelvin. So anyway, there's some unit conversions involved. I'm not going to go ahead and go through those. You can always, you should be careful with them and work them out, but just for the sake of time here, I'm not going to work them out. I'm going to assume that you can figure out the unit conversions on your own using a unit conversion table or using Google, for example, to do the conversions. But in the end, what you'll get is that the time that it takes to change temperatures is 47 minutes in the end. All right, so this is, just to kind of recap, this is a first law analysis, but it's a first law writing it out as a rate, in the rate form, as opposed to just a before and after form. And then we made use of the fact that the milk is assumed to be incompressible, so we could write out how the change in internal energy or specific internal energy is related to temperature. And then there was a little bit of math involved and some ugly unit conversions, but they can be done. Just you have to be careful with them. And then we solve for the time. So we'll end it there.